Okay, everyone, welcome to week 18 of quantum field theory. It's hard to believe we're 18 weeks into this. That's kind of crazy. Today, there's a lot of very beautiful aspects of the subject, but I think today is one of the more beautiful aspects because today we're going to talk about electroweak unification. And this was really the first. By the way, full disclaimer, there are a lot of bad calculations when it comes to what I'm going to talk about today. I'm not going to do them on the board. I'm going to show you my neat results that I got. You must check them, okay? Because they were very tedious calculate, not hard, but tedious. But before I get into the gory details, I think I should tell you what we mean by unification, right? That seems to be like a buzzword, but people don't seem to really understand what is meant by that. So you have the weak interaction, right? And you have the electromagnetic interaction. Now, unifying them from a technical point of view means writing all of the possible interactions of ENM, all of the mathematical structures of QED and ENM, and combining those mathematical structures with the structures of the weak interaction. That's what we mean by that. That means writing the theory as one Lagrangian, right? In the most broad sense. And what we should see is, first of all, the symmetries of QED should carry over, right? Entirely. The physics of QED should carry over entirely. And what we should see is that we can recover all of that same machinery from one singular Lagrangian. That's the whole point of unification. Now, physically, what does that mean? Physically, that means something quite interesting. Because, see, unification implies that the weak interaction and electromagnetic interactions are the same thing. They're not, right? They operate at different length scales. That's just the first thing you learn, right? When you learn about the fundamental forces, right? They are separate. So what we mean by unification is a mathematical unification, that they obey the same symmetries, that they come from the same structure, and that we can write them as one object, okay? That's what we mean. That's important to stress because it's not like they're the same thing, they're the same phenomena, right? Remember, the weak interaction is an axial vector coupling, right, versus a vector coupling of QED. We're going to see that the gauge fields that we derive are massive gauge fields, not massless gauge fields, right, like in QED. Okay, so there are differences and quite big differences. We are also going to see, and really what the beauty of electroweak unification is, this is your first example of actually seeing all of the different pieces of QFT sort of come together and predict things. Okay, we're going to predict a massive W and Z boson, and we are also going to see that the only way you can get a massive W and Z boson, in fact, the only way you can get the weak interaction to fit consistently with the electromagnetic interactions is to have your fields, your weak fields, coupled to what? Coupled to the Higgs field. So this will be our first introduction of the Higgs field. In the pop science, they say the Higgs field gives everything mass. That's not true, okay? The Higgs field only gives leptons mass, okay? So that these are the subtle things that they don't say, but because the Higgs field only comes into the story when we look at electroweak unification, okay? So I hope you remember spontaneous symmetry breaking somewhat because I'm gonna gloss over some of the details, okay? So let me give you your homework and then we'll get started. So the homework this week is Srednicki's book, has really good stuff on gauge theory, non-abelian gauge theory. I'd like you to read 69, 70, and 71. Also, Jenna, can you find the chapter? This is on non-abelian gauge theory. Can you find the chapter in here on chiral gauge theory? Chiral, because I want you to, because QCD, you can get QCD from chiral gauge theory as a starting point. So I want you to read about that, but I don't remember the chapter. Now, if you find Srednicki to be too difficult, start with Lancaster-Blundell, okay, and then go to Strednicki, because Strednicki is one of the, the big boy books, so to speak. So it's hard. It's a hard book. Like Schwartz, I'm sure that those of you that have been looking at now some of the big boy books know what I'm talking about, right? Okay. And if you really want to challenge, I would read Cheng and Lee, chapter 11. That's on electroweak unification, and that's how I learned about it in my particle physics class. And this was a really hard chapter to read. So I don't know if there's a PDF of Cheng and Lee online. If there isn't, just let me know, because I've scanned the whole book. Yeah, it's the Bible, so I figured I'll scan it. So, okay. So if you just want to look at like sort of the really like the way the pros talk about it, so to speak, go for it. It's a good instructive thing. And I hope you looked at from last week, the Fermi paper and not the Fermi paper, the Feynman and Gelman paper. Were you able to find those? Or no? Okay, I can send them to you. I have them all in a file, in a folder. I have all these papers saved. In fact, sorry?
In Strednicki, chapter 75 is chiral gauge theories and anomalies.
Okay, perfect. Yeah, so read 75.
What it also says a prerequisite for it is chapter 72.
And what is that on?
The Feynman rules for non-abelian gauge theory.
Okay, good, perfect. Because I'm actually gonna have you derive them. It's not for f squared, but I'm gonna make you do the calculation I just did, deriving them for f cubed, which I did it. I finished it. It came out well. Now I have to type it up. That's the tough part, the annoying part. Okay, yeah, read that too then, because that will be important. I just want to see if you can derive Feynman rules from Lagrangian. Okay, good. Okay, great. Strednicki is a great book. It's a really good book. In fact, it's become kind of the standard in QFT. That and Schwartz, with Z as like bedtime reading. That's sort of the prescription people have been using recently. Okay, excellent. Yeah, Strednicki is a good book. Okay, let's get started. So the starting point is to review gauge symmetry. Okay, so let's just review gauge symmetry and gauge invariance. Okay. So remember, we want the Lagrangian to be respect to local gauge transformations, right? And one way we can prove that the Lagrangian is invariant with respect to local gauge transformations is by doing what we always do in physics, acting on the Lagrangian with infinitesimal gauge transformations, right? That's what we do in physics. We act on something infinitesimally, just deviate a little bit, and we prove that it stays invariant. That's the standard way to do these kinds of things. So the basic idea, you take psi, some fermion field to 1 plus I alpha times psi, right? That would be an infinitesimal gauge transformation. Right, you take d mu psi to some d mu psi. I'll give you a second to think about what that would go to. Plus I, right? D mu alpha psi, right? And then the derivative is going to hit the other thing. So plus I alpha d mu psi, right? That would be the infinitesimal gauge transformation for the space-time derivative. And then for the gauge field, A mu would now go to A mu minus I over Q, where Q is like some charge or coupling, or actually this should probably be a factor of 1. I'm not even really sure. D mu alpha x. And so those are just the infinitesimal gauge transformations spelled out. And so the proof goes as follows. If we take some Lorentz scalar, psi dagger psi, right? So this is just a Lorentz scalar, right? This combination of spinor fields. And you act on it now with a infinitesimal transformation. I'll give you a second to write down what you would get, or the expression. So you're right, you're going to get psi dagger minus I alpha psi dagger, right, times psi plus I alpha psi, right? And you should find that this should equal, if you multiply everything out, you should just get psi dagger psi plus order alpha squared terms, right? Plus higher order terms. Okay, you can do that as an exercise. Multiply everything out. I'm not going to do it, but that's the basic idea, right? That should be invariant under that transformation. Now we know our derivative is not invariant under this transformation, so I'm not even going to bother writing this guy out. So what substitution do we have to make to have a locally gauge invariant object? Can someone remind us? It's the prescription of minimal coupling, right? That's the Jenna, you were going to say it, but
Covariant derivative.
right. So we have now a covariant derivative, exactly. That looks like that. And now this will be invariant under a local gauge transformation. Okay. So one can show the following very simply, that d mu psi dagger, d mu psi, again, if you multiply this out, you take the complex conjugate, you'll get the same combination back. D mu psi dagger, d mu psi, plus order alpha squared term. So again, this guy is locally gauge invariant, but our standard space-time derivative's not, simply because you're going to get this extra junk, right? Since alpha depends on x. Okay, so let's write down a Lagrangian for abelian U1 gauge theory. Okay, remember, U1 is an abelian group. Okay, the rest of the standard model, SU2 and SU3, are non-abelian. Well, they could be abelian, but the way we use them, the generators are non-abelian. They don't commute. So let's write down just a Lagrangian for U1 gauge theory with a complex scalar field. So a coupling of phi, psi bar, psi. No, psi dagger, psi. So then we just get the Lorentz invariant combination. So d mu phi dagger, where this d mu now is the gauge covariant derivative, d mu phi, right? So now this is our Lorentz invariant quantity, right? In gauge theory, or if we want local gauge invariance, it's not your standard space-time derivative, right? Minus m squared psi dagger psi. So this looks like Yukawa theory now, or just scalar Yukawa theory. And if I want to couple it to electromagnetism, then I have minus a fourth F mu nu F mu nu, where F mu nu is the field strength. Do we know how the field strength looks, or should I write it down again? Right, so just in this case, I'll just write it down because it's defined in different ways. This is d mu a nu minus d mu a mu. Okay. So this is scalar QED, right? Is there an interaction here? Is no interaction, right? Because there's no combination between phi and psi. And I have programmed local gauge invariance from the get-go because I have this combination of Lorentz of the scalar fields with the gauge covariant derivative. And I've also coupled it to electromagnetism. Okay. So this procedure now of taking d mu, recall that this procedure of taking the space-time derivative to the covariant derivative is called minimal coupling. Okay, so this is a minimally coupled Lagrangian with U1 local gauge invariance. Okay, is that okay for everyone? That should be a review, really. Okay. Okay, now let's write down the SU2 counterpart of this. So we did a lot of this a few weeks ago, so I'm not really gonna go so slow. So if we have d mu psi, let me just define the covariant derivative. How do we write this down now? So what is the covariant derivative on psi? So you can work out the exercises on your own. All right, so that's just d mu psi, right? The basic thing, plus iq a mu of x. This term, this extra iq a mu of x is often times called, or the extra junk you get is often called a gauge redundancy. If you're reading a paper, they often call that thing. And you know, in normal Feynman diagrammatics, there's a lot of gauge redundancies, right? The whole approach is dependent on your choice of gauge. Okay, that's part of the motivation for the scattering amplitudes program. Can you get rid of all the gauge redundancies, right? And start with a more fundamental picture that relies on mathematical principles or physical ones. Okay, again, a local gauge transformation just means that psi goes to e to the I alpha of x psi. Okay, but just a quick review so we're on the same page. And again, the gauge transformation in U1 gauge theory means that A mu goes to A mu minus what? Minus 1 over Q d mu alpha. And that's the gauge that's how the gauge field transforms in U1. We discussed this 2 weeks ago, right? I showed you how the gauge field transforms. Okay, so let's write down an SU2 Lagrangian for fermions. Of course, it's going to be non-abelian now, right? Only U1 is an abelian theory. Okay, so what are we going to get? The Lagrangian is just psi bar, right? So now I'm going to write one just for fermions. I gamma mu d mu minus m. Okay, right, minimally coupled. Psi, so the Lorentz invariant product is still psi bar psi. Okay, minus a quarter. And I'm going to tell you what these capital G mu u's mean. No, it's not the Einstein tensor. It's just a different notation. Remember, recall, this should be a recall now that in SU2, the covariant derivative goes to what? Now d mu psi. But now my dependence is on another parameter, right? i.e. the Pauli spin matrices, right? Those are the generators now of SU2. So this is going to this should be a minus. This is going to transform as minus, let me think. Right, I over 2 G tau. G is a coupling now. Again, G is just some coupling. Dotted with the gauge field. Right, this should be a familiar thing, right? From last week and the last several weeks, we've seen expressions like this. Even from QED, we've seen expressions like this. And now the G mu nu, not the Einstein tensor. I should use a different letter, but whatever. We're going to have a lot of letters today, so I kind of run out. Now G mu nu is the analog of the field strength, but now it's going to be gauge corrected. So this is d mu a nu minus d mu a mu minus I a mu. Right? Now we get this correction. Oh, actually, wait a second. This should be G, and actually, someone needs to check this for me. I think it's A mu times A mu. Oh, sorry, that should just be it. But check. When I tried doing it, maybe I did it wrong. Actually, I think it's this. I think because in the Lagrangian, you take a trace of F mu nu. That's why they put the commutator, because you end up with this combination anyway. Right, because like the Lagrangian and non-abelian gauge theories minus a quarter the trace F mu nu, and since you're taking the trace, one can show that this just becomes d mu a nu minus d mu a nu plus G FABC. Right, this would have an A, this would have an A, AB mu, AC mu, right? This comes from the trace though, the trace of F mu nu, right? So that's why you just get a combination of A mu, A nu, right? Instead of the commutator. That's based on what I don't know. Okay, whatever. You check that. Okay, is everyone okay with all of that, or Are we rusty or anyone have questions? Now's the time to ask because it's going to get very heavy on this in 5 minutes.
G is the coupling, right?
Which G? Little
Oh, the
g or big
lowercase
G?
one.
Little g?
Yeah,
That's the coupling, yeah.
right. So what's tau?
Tau are the generators of SU2, the Pauli spin matrices.
Okay.
I should call them sigma, but actually a few QFT books call them tau. Very strange, so I don't know.
Yeah, Lancaster Blundell called it tau.
Tau, really? Okay. I should do more careful reading of that book. I think there are errors as well. But I'll take a look. Okay. I think actually Srednicki covers this in chapter 69. In Srednicki, one of the non-abelian gauge theory. I know Weinberg covers it. That's how I learned it. But I think Srednicki covers this too somewhere. How to get from this Lagrangian to this expression. It's not trivial at all. Okay, so now let's talk about what we want to describe. Does anyone have any ideas? Like if you were sitting down and you said, okay, I want an electroweak theory. What particle interactions do I want to describe? Like what is the best way to describe it? Or what are the kinds of interactions we saw last time? Like at the most basic level.
We want the fields to interact with the Higgs field.
That's not obvious though, right? If I didn't tell you that, you might not have known. So what particles do we, that's a good guess though, but what particles do we want to interact? Like what would be the phenomena that we want to interact? Do we want quarks? Okay, right. So that's what I mean. So what phenomena do we want? Do we want neutrinos? It's the weak interaction, right? So we're going to need neutrinos and we're going to need some kind of leptons. Okay, and the easiest lepton to use is the electron, right? And then you can easily just put in any other mass of any other. So we're going to write a Lagrangian with the electrons and neutrinos. Now, actually, the way we're going to write out the Lagrangian is in terms of three fields. Now, you may remember electrons have two different spins, right? Now, one way, as you know, to look at this is in terms of something called chirality, okay? We can say that electrons come as right-handed electrons and left-handed electrons. Okay, chiral comes from the Greek word, I think it's Greek, for handedness. This becomes a very nice mnemonic to describe the weak interaction because neutrinos are only left-handed. What do I mean by that? They only come in one type of spin, actually. That's kind of interesting. Neutrinos do not have two different spin states. So this is why this becomes a nice way to divide these. So let's write down a Lagrangian now. And let's just be careful. Like what I'm going to write down now, both the electron and the neutrino are going to be massless, okay, in this Lagrangian. Is the neutrino massless? Yes, right? Well, for our intent, basic, we're theorists, so yeah, for us it is. And is the electron massless? No, okay? So somehow, and this is where the Higgs field will play the role to give the electron mass, okay? Okay, so let's write down just a basic expression now for the Lagrangian to kick off this party. So I'm going to have some, I don't know, V bar E of X, right? So now this is the neutrino field, okay? I V slash the VE of X, right? So the V bar again is the standard adjoint. V bar L of X I D slash L of X, the left-handed electron field, plus, you guessed it, the right-handed electron field. Oh my gosh, what am I doing? Wait a second. Wait, do I want the adjoint to be the left-handed field or? Oh no, I was doing it right. These should both be the left-handed fields. These should. Yeah, I was doing it right. Okay. Everyone knows what the slash is, right? This is Feynman's stupid notation, where the slash, I'll remind you, the slash, d slash is just d mu gamma mu. Okay, that's Feynman's notation. I will not tell you the story of C and Yang's students who could not understand Schwinger, and the only thing they learned from the conference was Feynman slash notation. It's a nice story. Okay, in this theory, we're going to need conserved quantities, right? I think the basic conserved quantity we're going to need is a charge. Now, contrary to your intuition, we don't use the standard charge here. We're going to define a new kind of charge because of the way that everything is organized, okay? And it's not going to make sense now. It's going to make sense in half an hour. So I want to define a quantity. So now Q, my charge, is going to be equal to I3 plus Y over 2. You might recognize these I's and Y's. Yeah, you might recognize the I's and Y's. This is called the Gelman. This Gelman discovered this, but who was the other guy? That's not good. Gelman, if you want to look it up. Gelman-Nishina, something like that, relationship. The guy who came up with the Klein-Nishina relations, those really annoying things we were writing a few weeks ago. Okay, why am I writing the charge in terms of new variables, I3 and Y? You'll see. These are going to be isospin and hypercharge. Totally theoretic, made up, okay, stuff. Okay, so now we're going to write down the fermion field in the following way. So psi of x now becomes now a vector with the neutrino field, the left-handed electron field, and the right-handed electron field. Okay. And now the gauge field is going to transform with this new definition for the charge, because remember, we have a Q in the transformation, A mu of x plus 1 over yg, because now this hypercharge is going to have to play a role, d mu alpha of x. Okay. Okay, and my gauge transformation is now e to the I over 2y alpha of x. Where now I can define a charge Q as some y of E. Now it's a function of y instead of a function of big Q. Okay, what is y? Y is called weak hypercharge. These names are crazy. You're going to see why we introduced it. You see, okay, you want me to give you, these things seem very mysterious, right? We hear these words. Let me just give you a 1-minute rant about why we use them. It's going to be very shocking to you. Actually, not really. You know, group theory is basically a way to represent things and organize things. That's all it is. That's why people called Gelman the Mendeleev of physics, right? Mendeleev, the guy who discovered the periodic table. Discovered, no, but put it into the periodic. oftentimes to fit things into a certain group structure or picture, we introduce new variables or degrees of freedom to classify things. Okay, hypercharge is one example of that. Now you say, how does this translate physically? Well, I can figure out Q in the lab, right? I'm not going to figure out Y or I in the lab. Those are not things. Okay, I'm going to figure out Q in the lab, and Q comes from combining Y and I, right? Now I can sort out the left-handed, right-handed fields in terms of Y and I. Okay. Now I've organized that, but now you see, to the theorist, Y and I are very important, right? Because to the theorist, Y and I fall into the representation. And we want that symmetry. We look for that organization. To the experimenter, Y and I mean nothing. Okay, because Y and I, in fact, I remember having this discussion with my friend. Some experimenters audited the particle physics class. They didn't take it because it was for theory students, but they just sat in. And we just learned about Y and I. They were like, what is Y and I, you know? And I told them in the, we were eating dinner in the evening, and I told them, Y and I should mean nothing to you. They only mean something to us because we wanted to fit some representation. Okay, so just keep that in the back of your mind, okay? Okay, so to that effect, Y is called the weak hypercharge. It's U1, it's a U1, it's a U1 piece, right? Because look at the gauge transformation. This is a U1 gauge transformation, right? Right? Now, Y is the parameter or the generator, or yeah, the constant. It's a constant. It's not a generator. Y is a part of the U1. No, it is a generator, basically. But U1 is weird, right? Because U1 is just a number. So it's weird to call something a generator, but it's just a constant, right? You're multiplying by a constant. That's what U1 symmetry is, right? Okay, so it's a U1 piece. And now the electron neutrino, or any neutrino, has a hypercharge of -1. Left-handed electron field has a hypercharge of -1 or 1. No, it's got to be minus. And then the right-handed electron field, therefore, hypercharge of -2. Again, you can get the charge from this relationship, right? Derived by Gell-Mann and Nishida. This is the piece. This is what they care about in the lab. This is the charge, right? They have a charge. These two pieces are to fit our mathematics, okay? And it's not just, I just want to be, it's not just fitting the mathematics. The mathematics, by fitting the mathematics, you make predictions. By fitting the mathematics, they predicted a massive W and Z boson. I ask you, did they know that a W and Z boson existed when they predicted it? No, right? They had no idea. That's the beauty of it. That's why we wanted to fit the mathematics, because it makes predictions. Okay, it's not just like I'm sitting there going, I want it to fit SU3. It must fit SU3. No, that's like the stupidest thing ever, right? We wanted to fit SU3 because it makes prediction. It predicts massive W and Z gauge bosons. It predicts coupling to the Higgs field. Okay, it makes these amazing predictions that somehow are true. Okay, just remember that. That's so important. It's not just saying, oh yeah, we're not mathematicians, okay? We don't care that it could fit some random structure. Who cares? We're not mathematicians. Okay, so let's just spell this out. So then we have, so this is how this is going to transform. Okay, now this is going to have a U1 gauge transformation on it, right? Where this is just e to the -I alpha of x over 2, 0, 0, 0. I'm just going to call this guy rho. So this is rho 0, 0, 0. Just so I don't have to write this 3 times on the day. Okay, so this is called U1 weak hypercharge. Now, those of you that know your group theory, you know that SU2, you know that the Electroweak theory is SU2 cross U1, right? Or it's a U2 gauge theory. Therefore, weak isospin must be in SU2 symmetry. Oh, which makes sense, right? Spin, Pauli spin, this is just some analog of that. So that's the thing, Pauli spin will not fit into an SU2 cross E1 representation. Isospin will, that gives you the right charge, okay? Okay, let's write that down. So SU2 weak isospin, let's write down the transformation. It's going to take a nice, very simple form. Okay. So now this guy, so VEEL, the right-handed electron does not have any isospin. It's going to go to E. Do I want to use tau? Let's just use tau for consistency's sake. I/2 tau dot alpha of x. SU2 weak isospin. And E right goes to E right. I'll just write that down. Okay. And we write down I, so, and I3 is like the Z component of isospin. So there's three components. You know we have to pick one like component to focus in on, so we don't use all three. So conventionally we use the Z axis, so I3 in the 3 direction. So what are they? It's so for the neutrino, it's a half and a half. For the electron, it's a half and minus a half. And for the right-handed electron, it's 0. Okay. That's the isospin. Okay, so let's write down now a U1 transformation. So now what is the U1 transformation going to look like on the covariant derivative? Well, d mu psi is going to now equal d mu psi partial, right? Minus I/2 G, we'll call this G prime. It's going to be a different coupling, okay? The U1 is going to have a different coupling. That's what we're going to see. Y d mu of x psi. This is anticipation of the fact that actually the coupling to the W and Z is different. It's not exactly the same. It's very, very close, but it's not exactly the same. Okay, and now the SU2. Like, this is just analogs of things we've done, right? It's just a little bit different so far. All right, same idea over and over again. Minus I, G, I, tau. Wait a second, did I forget the, right, sorry, I forgot the I. Sorry, up there. That's important, right? Otherwise, we'll call this field W. Oh, this should be a dot as well, dot with the B mu. So these are the two gauge fields, W and B. We're going to have a lot of gauge fields, right? Because it's just, I don't know, B, we might discard the B, but just, they're all the same. They're all different in certain ways. Okay, now this is a very beautiful conventional way that every quantum field theory book has adapted now. Quantum field theorists have adapted now, where we write down now psi, just to simplify the writing, as a field, a 2-component vector of L and R. Okay, this is just the convention, right? Where you guessed it, L equals the neutrino and the left-handed electron, and R just has ER. Okay, and just a way we've simplified our expressions. So now d mu capital L. And this is convention everywhere, okay? So I'm not making it up. D mu L minus I/2 how would this work itself out in this new language? G tau dot W mu L plus, and now we need the electron piece as well. Or sorry, we need the, yeah, we need the other piece, sorry. We need the B mu piece as well, plus I over 2 G prime tau dot B mu
Is there supposed to be an I in between the G and the tau?
Yes, sorry. Yes. Oh, yes. No, a Y here and an I here.
Okay.
Right? Because this is the U1 piece, this is the SU2 piece. Yes, exactly. Because now the right-handed field is not going to have an SU2 piece, right? It's only going to have a U1 piece, right? Because the right-handed electron has no isospin. Okay. So let's write down d mu r. I'll just write it down here. And now it's only going to have a right-handed piece. So d mu r, very simply now, is just d mu is just d mu r, right, plus I g prime y mu r. Yeah. Everyone okay with that? Okay, let's write down a locally gauge invariant Lagrangian, right? That would be the next natural step, right? Now that we know the transformations. Okay. This is why, folks, when you take QFT1, when you take it in college, or if you you already know QFT somewhat, but but the structure of the formal class, they teach you up to QED. That's usually QFT1 because you guys just start, once you know QED, the rest becomes very technical aspects of the subject, right? It's about knowing QED. Okay, let's write down the Lagrangian. So now the Lagrangian is R. We have this R guy here now. I gamma mu. This is for Isha. I'm not going to use slash notation. Only for Isha. D mu plus I G prime mu. Oh God, this should be R bar. R, right? R bar, right? Because R bar R is still, yeah. Plus L bar I gamma mu. We're just really rewriting it by rephrasing things and making it locally gauge invariant. D mu minus I over 2 tau. This should be a dot, but it's implicit that it's a dot when you're multiplying it. Dot W mu plus I G prime dot B mu. I'm going to stop writing the Y's and the I's, okay? That should just be implicit now because I keep forgetting them, so. L minus a quarter, and we have the same field strength, the gauge invariant field strength now. So this comes from SU2. I'm going to put the superscript W for a reason you'll see in a second. G mu nu W. This is coming from SU2. And from U1, we have minus a quarter F mu nu B F mu nu. B, this is to signify that the F mu nu's go with the B fields, right? What we're calling the B fields, right? Because they're coming from the U1 symmetry. And the G mu nu's, not the Einstein tensor, go with the W fields, which are coming from the SU2 symmetry, the isospin and hypercharge respectively. Okay, so I'll be explicit about it. F mu nu B is just d mu minus d mu b mu, and g mu nu of W is just d mu W mu minus d mu W mu minus I W mu times W mu. Sorry, plus G, right? We want the coupling. Sorry, plus G. Okay, we're getting there. We're getting there. What should we do next, guys? I'm joking. It's not obvious at all. We're getting there. So the next step, let me see. What should be the natural next step? So we want E and M and the weak interaction embedded in the same Lagrangian, right? And this is kind of close, right? It looks pretty good actually. It's an SU2 cross U1 Lagrangian. It's describing, it has no interactions though, right? Okay, so we want interactions. This seems like a free Lagrangian to me because I have no vertices. I have no Feynman rules here. I have no vertices between electron fields and neutrino fields. Okay, so that maybe we want, I don't know, do you guys just want a free theory? Okay, that's ambitious. So we don't want just a free theory, fine. We also, the electron is still massless. I really haven't even written the letter M here. That's probably bad. But before we continue, let's write down some conserved currents, okay? Just because that's kind of the natural thing to do, I think. So the conserved current, you can find the conserved current now using the equation we learned, I don't know, in week 2 of the class, as the conserved current now, or the weak isospin current is 1/2 L bar gamma mu L, something like that. I think you need a tau. You check that. Okay, and now I'll leave it as an exercise for you to get the other current, the SU2 current. So what is J mu SU2? If not, we can discuss it tomorrow morning. That's not something. I think I must have given you how to calculate this in like week 2 of the class, and we talked about symmetry. Yeah, there's no way I didn't. Okay. Okay, so let's continue. Let's press on. So now the question becomes, we want interactions and we want masses. So interactions we'll get by coupling the neutrino with the electron, right? And we'll get a Feynman rule for the vertex. Easy. And we can read that Feynman rule off the Lagrangian. How about, and by doing Wick contractions, oh my God, oh no, everyone is freaking out now. How about mass? We're gonna have to couple to something else to get the mass, and that is our famous Higgs field, right? And the goal is to have the Higgs field give mass to the electron. If you recall from spontaneous symmetry breaking, when we learned about it, the consequence of spontaneous symmetry breaking was what? The first consequence of spontaneous symmetry breaking were Goldstone modes, right? And Goldstone bosons, which were just artificial gauge redundancies, right? Which we got rid of. They were like fake particles. What was the second consequence of spontaneous symmetry breaking? It's our very famous A mu. The consequence was a massless gauge field, right? That also came as part of this situation. Now the gauge field ought to be massive, okay? That's a prediction this theory will make because the electron is massive. The photon is massless, okay? So the mediators are going to be massive, okay? So let's write that down. So let's start with the Higgs. So the Higgs is a scalar field, okay? And we write it as this so-called Higgs doublet, okay? So we write it in the following way. We write it as some phi plus phi 0. These are just definitions. I'll describe them in a second. Where this guy is now 1/√2 normalization. And these are linear combinations of components of the Higgs field. So this is phi 3. It's phi 4. Actually, it's a plus. I'm thinking the minus. Okay, and one can derive that phi dagger phi, or one can show that phi dagger phi, if you just take that scalar product, is just 1/2 sum from I equals 1 to 4 of phi I squared. So these guys are like complex vectors, right? That's what a field is to a certain extent. And you can rotate them. And when you take their inner product, you get a distance, you get a length. Okay, that's how they work. This is called a doublet. This is a doublet, right? Because there's two possible states. It's not a singlet, it's not a multiplet, it's a doublet. Okay, for the Higgs, has a weak hypercharge of y equals 1, and isospin, a weak isospin of a half. Is that a minus or plus? Nope, it's a plus. And so let's just write down the transformation. So again, the U1 transformation goes to what? Well, now it's going to be a 2x2. A 2x2 matrix. So e to the I alpha over 2, 0, 0, e to the I alpha over 2. And similarly, the SU2 transformation is just e to the I over 2 tau alpha times 5 plus 5, 0. Okay. So that's how the Higgs transforms. Dot alpha. Okay, so the Higgs is like, it's the same. It's just a scalar particle now, right? And when we imply, when we use spontaneous symmetry breaking and we spontaneously break the symmetry of the Lagrangian, the Higgs field will give the electron mass. So that's why Salam and Weinberg took Glashow's initial idea and called it a spontaneously broken gauge theory. Okay, that's really, whereas QED is not a spontaneous, you don't have to break any symmetry, right? Because the photon field is massless. And that just comes from local gauge invariance. Anyways, let's press on. Okay, now, of course, what is the next step? Does someone want to tell me, or intuitively, what should we do next? Or should I just write it?
Couple the Higgs field to the other ones, to the other fields.
Yeah, that would be a wise thing to do. But before we do that, you're good. You're going 2 steps ahead. Let's just write down how the covariant derivative acts on phi. Yeah, okay. So let's just do that. I'll just give you that expression. But you're right. We have to do that. That's the final step. Okay, so d mu phi, I'll give you a second to write this down. Or write down what you think it should be. The Higgs. Can you believe that this was predicted in the 1970s by Peter Higgs? Actually, no. Yeah, no. Yeah, late 60s or early 70s by Peter Higgs. And then Glashow, Weinberg, and Salam applied it to electroweak unification. Isn't that crazy? 40 years before they found it. Wow. I can't imagine the thrill, right? But it makes that analogy that the Higgs is like molasses. It's so wrong because it doesn't give mass to everything. It only gives mass to the electroweak sector. Yeah, are you guys good? Do you have something written down somewhere? Okay. Okay, so right, this is just d mu phi. And now I want to program the SU2 and U1 symmetry. So I get I over 2G tau, something like that from the SU2 symmetry, dotted with W. That's what we've been calling the SU2 field. Okay. Right, and then minus I over 2G prime d mu on phi. Okay, that's it. And so now I can write down a Lagrangian for phi. It's going to have other terms because it needs to couple totally to the lepton fields. So I'm going to get some d mu phi dagger phi. Right? That's the natural first combination. This is all locally gauge invariant plus m. We'll call this mh for m Higgs. Over phi, and we'll also add some lambda over 4 term because it's gonna couple and create interactions, right? So we want the whole Higgs part of the Lagrangian to have some kind of interaction. Right? This on itself is not an interaction, right? Because phi dagger and phi don't create, they can't couple to each other, right? It's not, they're not phi fields, right? It's not like in phi to the 4th theory, right? Our first interacting theory where you have 4 phi fields. Now this is phi dagger phi. They're the Hermitian conjugate to one another. Okay. Okay, and we only implied this condition that the minima of phi is not 0. That's how we're going to get mass when we take the minima. That's the broken symmetry procedure, right? When we spontaneously break the symmetry, we find the minima and use the minima of the potential. Okay, now let's write down a full interaction term for the Lagrangian. So what will be our interaction term? Coming from this lambda term, now it's going to be like minus some coupling. We'll call this GW for G weak. L bar phi r. So now I have an interaction between phi r and L bar plus R bar phi dagger L. Okay, this is the best part, right? This is going to tell us all the interesting parts of the theory. All right, now we can write down the full Lagrangian for Glashow, Salam, Weinberg theory. We're ready, and then we can see what it predicts. Okay, so it took us an hour. It took us an hour and 20 minutes to write down just the Lagrangian. Forget about working out its details. So we might have to do that next week for a little bit. Actually, no, I think we'll be good. Okay. Yeah, there's a lot of details to work out, right? Because you're all like, what about the Weinberg angle? I know that's what you're all thinking. So it's there, believe me, we're gonna get it. But let's just write down the Lagrangian. Okay, putting all of that together, what is the Lagrangian for the electroweak unification? And then we're gonna see how it works. Okay, the Lagrangian, the Glashow-Salam-Weinberg Lagrangian is L bar I gamma mu d mu L. So this is just my free left-handed field, or my free L field. We'll just call it the L field. Plus R bar I gamma mu d mu R. I'm so nice to Isha. I'm not using flash notation. I'm so nice to Isha. Plus, now the free part of the Higgs field, d mu phi dagger, d mu phi, free part of the Higgs field. It's m squared h over 2 phi dagger phi. Minus lambda over 4 phi dagger phi squared. So these are all of the extra terms of the phi Lagrangian. Minus G weak. So now our interaction term, right? L bar phi R plus R phi dagger. Wait a second. L bar, what was the interaction term? R bar phi dagger L, right? And then we get our field strengths, minus a quarter G mu nu, G mu nu. W minus a quarter F mu nu, F mu nu. That's it. Done. We haven't broken the symmetry yet, so we haven't done the actual important part. We've just written down the Lagrangian. Pretty cool, right? You can write down, like, if you showed this to your friends, you could tell them, like, this is it. This is electroweak unification for the most part, but we have to explore it. We've just been getting a ton of alumni email. They've already asked us to donate 5 times, just saying. Okay, cool. Okay. Okay, so we're going to need some symmetry breaking. And if you remember from my lecture on symmetry breaking, I asked you, shall we break the symmetry? To that which you all went, no, but we have to do it. Because that's the only way we can get the consequences. Sorry, which is, okay. Okay, so we want some SU2. So this is an SU2 cross U1 theory. We want some SU2 cross U1 symmetry breaking. This is technically a U2 group. For those of you that are really group theory nerds, you go look that up. Okay. So what should our minima be? That's the question, right? Because if we remember, spontaneously breaking the symmetry, just the basic procedure, right? When we did this, I want to say like 6 weeks ago or something, what we did was we found the minima of the potential. Okay, and that's what we input into the Lagrangian. And we got all those funky potentials, like the Mexican hat potential and kind of like weird ways in which the phi particles were behaving. And this is called the Higgs mechanism, right? This was called the Higgs mechanism. And then I told you, okay, we're actually going to use a Higgs field soon. So now we're using it. So now we just employ the same procedure. So the basic idea, we just want a minimum. And so we take the field phi and we excite it, quote unquote. We have some excitation. The components vary, right? Now that the linear combinations of the components vary, right, in the complex plane, and that's you find the minimum. So I'm just gonna, this was a very gnarly calculation. I'm just gonna write down the minimum, and you can do it or look in a textbook. Okay, so the excited field now, phi, it better be a one component field, right? The minima is gonna be in one component, okay? And so I chose it to be in the phi, in the bottom component. I don't remember what we called it, phi 0. Is that what we called it? Just now in the Higgs doublet, it was phi plus up top and phi 0 at the bottom. Yeah, okay. Okay, so 0, and I call this V. I'm going to tell you what all this is. V plus h of x over 2. You're going to see what these parameters are. But I've introduced 2 new parameters. Actually, I think the normalization is root 2. Okay, that's the minimum. Okay, you'll see how this works. Don't worry, I promise you. You'll see how this works. Okay, now we have all the pieces. We have the Glashow-Salam-Weinberg Lagrangian. We have the minima of the Higgs field. Now we just have to break the symmetry and we should be able to make predictions. So the first thing, let's look at the origin of the electron mass. Okay, let's see how the electron gets its mass. So let's do that. If my minima step was shady to you, watch my lecture on spontaneous symmetry breaking, and you should be able to get the same result. Okay. Or you could use Cheng and Lee and read like a 1-sentence explanation that drives you crazy for like a week. You could do that too. Take your pick. Okay. Okay, let's look at the origin of the electron mass. So recall the fermion Lagrangian, or just the free fermion Lagrangian, is psi bar p slash minus m psi in p space, right? And now I'm going to write psi as a linear combination of psi left and psi right. Remember, we did all of this. Right, and so let's expand this Lagrangian now. I'll give you a second to work that out. I'll just do it with you. So psi bar L P psi bar R plus psi bar L P psi bar L plus psi bar L P psi bar psi bar R P psi L plus psi bar R P psi R, right, and so on and so forth. So take a second to do that. Minus psi bar R M psi R minus psi bar R M psi L minus psi bar L M psi L minus psi bar L M psi R. Right, just multiplying that out. Okay, you get something that looks like that. Okay, let's just combine some stuff. So now I can write this in the following way. psi bar L P psi L plus psi bar R P psi R minus M. Let's see what I can factor out. Yes, psi bar R psi L plus psi bar L psi R. Okay. Okay, I just multiplied stuff out, okay. Are we good with this? Wait a second. We have a mass term now, okay, that we need to look at. So the mass term, so okay, this Lagrangian, you're gonna see why I'm using this. But now we basically why I did this, okay, why did I do this calculation? It's to show you what kind of combination of fermion fields do we want to correspond to a mass term, okay? That's why I did this. And we see that we want this kind of thing, okay, from our interaction term. Okay, that's the only reason I did this. There's no direct, there's no term in the Lagrangian like this in the weak thing that we wrote down, right? This is like a side. So I'll just aside. Just to show you the kind of combination we want, okay? Yeah. Can I erase the board? Okay. Okay. So let's look at our interaction piece. So Li equals GW. Oh my God, I forgot it again. L bar phi dagger R plus, yeah, R bar phi. Oh, wait a second. I'm pretty sure the dagger was here. Though I might be wrong. We'll find out in a second. Okay, now phi becomes the spontaneously broken field, right? With one component. Wait a second. L had two components. Why is the top component of the doublet 0? Because the top component of L is what? Which particle? L had two particles in it, right? That's how I made that little column vector. Which particle was in the top component?
The electron neutrino.
Exactly. And multiplied by 0 gives you no mass. Okay, it has no interaction with the Higgs field. Okay, so we use the broken symmetry excited state, and now we can write down this combination of L bar phi R. I'll give you a second to think about that. This is just going to be E bar L times V plus H of X over root 2, this spontaneously broken thing, times ER, right? Similarly, R bar phi dagger L is going to be now E bar R, V minus H of X over root 2 EL. Wait a second. What is the Hermitian conjugate of this? This is just a plus again. There's no complex term there, right? So the sign doesn't change. Okay, and now we can write down the interaction term. I'll give you a second to expand this or not. You're going to get minus GW. Can work it out. E bar L V E R. E bar R V E L. That should be your first term. Just doing it quickly. Minus GW, E bar L, H of X over root 2, E bar plus E bar L. Yeah, that should be good. H of X over root 2. Wait a second. E bar L E R. Yeah, this should be E bar R. Yeah. Sorry. Now we remember. The mass term had what kind of configuration? So in that little exercise, the mass term, okay, was proportional to some term that went what? Psi bar L, psi R, plus psi bar R, psi L. Which term has that configuration? So that's why we did that exercise for just a random fermion Lagrangian, right? Just to show you, like, what should the mass term look like? What combination? Which term is going to give me the mass now? Well, wait a second. They both will give you. Wait a second. Wait a second. Wait. Let me think about this for a second. E R E L E L E R E L E R. Yes, good. So the mass now for the weak guy is GWV times some guy V, okay, which I'll tell you. I don't know if we'll get to it today. Right, because I factor that out and then I get the combination E bar L E R, E bar R E L. Psi bar L psi R, psi bar R psi L. Okay, so we derived something for the mass now. Or you could use this, right? GW H bar H of X over root 2. Okay, so what have we predicted now? So we use that Lagrangian. We use the interaction. So this is how we work, right? We write down a Lagrangian for a theory. We did. Glashow, Salam, Weinberg, Lagrangian. And now we look at pieces of it and make predictions. The first prediction we made, electron is massive, neutrino is massless. First prediction. Okay. Next prediction we need to make, the prediction of gauge bosons. Okay, massive gauge bosons.
So could we also write the mass as GW H of X over root 2?
Yes, the parameters will work out. But we're going to have to work out some more machinery for that. Yeah. Okay, I'm going to stop there. I think this is a natural place to stop because it gets a little intense because we have to derive the gauge boson, the massive gauge bosons, and in doing so, we're going to derive the Weinberg angle, right? Or that parameter. Okay, and you're going to see where that comes from. And then from that, we're going to derive the masses of the W and Z, right? Which, as you know, are written in terms of sines and cosines of the Weinberg angle, right? So the Weinberg angle is kind of the big parameter in the electroweak theory. Okay, any other, so next time I will wrap up electroweak unification. We made big achievement today. You have now seen the theory. That's a big achievement. And now hopefully you can see all the moving pieces in that theory, right? SU2 cross U1 local gauge invariance. Interactions between lepton and neutrino fields. Interaction between the Higgs field, minimal coupling. There's so many pieces in that, right? So it takes a lot of machinery to even understand somewhat. Next week, I'll wrap this up. And after I wrap this up, I'm going to talk about chiral gauge theory, okay, which will be a nice, maybe even anomalies a little bit. Tell you what anomalies are. Okay, any questions for me? Okay, good work. And I'll see you guys tomorrow. Stop recording. Can stop the